So we have seen the characteristic parameters of asymmetrical networks. So we have defined what is iterative impedance, that is ZT. Then image impedance, ZI, iterative transfer constant, theta t, and image transfer constant, theta I. Okay. So how did we define iterative impedance? So we consider an asymmetrical network. Okay. So we have the input terminals 1 1 dash, and we have the output terminals 2 2 dash. Now we can attach an impedance to the 2 2 dash terminal, which is the iterative impedance with respect to this terminal. Okay, so this is our ZT2. Similarly, we can attach another impedance to the 1 1 dash terminal also, which is ZT1. So ZT1. Now, how we have defined these iterative impedances? So when you look at this network from the input side, okay, you are looking like this towards the right side. You are looking at this asymmetrical network with ZT2 attached to the 2 2 dash terminal. So the combined impedance, that is, you are looking in this direction. So the combined network impedance, that is impedance of this network with this ZT2 attached to the 2 2 dash terminal, it will be equal to ZT2. Okay, so that's how we define this iterative impedance ZT2. Okay, similarly, you look from the second port towards the left like this. Okay, with ZT1 attached to the input side. You are attaching the iterative impedance ZT1 attached to the 1,1' terminal. So what is the impedance that you get? The combined network impedance of this asymmetrical network with this ZT1 attached to the input side. So this ZT1 is attached to the input side. So that will be equal to ZT1. So that's how we have defined the iterative impedance ZT1 and ZT2. Okay. The second characteristic parameter that we have defined is the image impedance. Zi. So if we consider an asymmetrical network, again you can draw the input port 1,1' and you can draw the output port 2,2'. Now we are attaching what we call the image impedance. So I am attaching the image impedance Zi2 to the 2,2' terminals. Okay. Similarly, I can attach another image impedance to the input terminals 1,1'. Let it be Zi1. Now this is Zi1. Okay. So how we have defined Zi1 and Zi2? So to understand that, let us look at the network from the port 1 side, that is the input side, and like this. So we have this asymmetrical network to which we have attached the input to which we have attached the image impedance Zi2. Okay, so we have attached this Zi2, and what is the impedance that we see from the input side? So what is this impedance that we get when you look at the network, combined network, this one plus the Zi2 attached to the 2,2' terminal? So this impedance will be equal to Zi1. So that is the image impedance that we see. So we have defined an impedance Zi2 which when attached to this 2,2' terminal, and you look at the network from the input side and you get an impedance Zi1. Okay. Now you look at the network from the other end, that is from the output port towards the left, with Zi1 attached to the input side like this. So what is the combined impedance that you see from the second port with Zi1 attached? So it will be the combined impedance of this asymmetrical network as well as this Zi1 attached, and you should get this impedance as Zi2. Okay, So this is the definition for image impedance. So when you attach the impedance Zi2 to the output side, and you look at the network from the input side and you see the impedance Zi1. Similarly, when you attach the same impedance, this Zi1 to the input side, and you look at the network from the output port and you see the combined network impedance as Zi2, then you can say that Zi1 and Zi2 are the image impedances for this particular asymmetrical network. Okay. Now there is one more equation which could be used. There is an equation which could be used to determine the values of Zi1 and Zi2. So Zi1 could be written as square root of Z SC1 into Z OC1, where ZSC is the short circuit impedance and ZOC is the open circuit impedance. Okay, so what is ZSC1? ZSC1 is the we have the network like this. So this is our asymmetrical network. And we are looking at this network from the input side. Okay, and we are trying to find out the image impedance with respect to this input side, that is 1 dash terminal. So this is 2 dash terminal. So when you look at this network from this side and then you short circuit, you can do the short circuit of this port, output port, that is 2 dash terminal, then you will get the ZSC1. Okay, now you remove this short circuit. You can remove this short circuit and open it, then you will get the Z open circuit with respect to the 1 dash terminal. Then you take the geometric mean of these to get the image impedance Zi1, that is the image impedance with respect to port 1. You could obtain like this. Similarly, you will be able to write the image impedance with respect to port 2 Zi2 as the geometric mean of the short circuit impedance ZSC2 into open circuit impedance ZOC2. So this method also you can do to find the respective image impedances. Okay. So what is Zi2? Zi2 is root of ZSC2 into ZOC2. So how you will get? So you take this network, same network, and look at this network from the 2 dash terminal. Okay. So in order to find ZSC2, you have to look at this network from this side and you do the short circuiting of this side. Then you will get ZSC2. Similarly, you remove the short circuit. You can remove this short circuit and you will get the ZOC2. Then you take the geometric mean of these two quantities to get your image impedance with respect to port 2, that is ZI2. Okay, so this is another method of finding the image impedance. The next parameter that we have seen is the iterative transfer constant, that is theta t. So to define this, we need a asymmetrical network. Now this network is terminated by its, okay, we have the input port 1 dash and the output port 2 dash. Now this network is terminated by its iterative impedance is a T2. Okay. Also we have the sending end current IS and the receiving end current IR. We have the sending end voltage Vs across 1 dash terminal and the receiving end voltage VR across the terminal 2 dash. Okay. Now we have defined the quantity e power theta t as the ratio of the sending end current IS to the receiving end current IR. Okay. Now when we look at this network from this side, that is the input side, we look towards the right. So what is the impedance that we see when you look like this? So the net impedance of this network plus this ZT2 attached to the second port, as per definition of iterative impedance, this will be equal to ZT2 itself. Okay, so we can write as e power theta t is the ratio of the sending end current to the receiving end current, which will be the same as the ratio of sending end voltage to the receiving end voltage. So we define the iterative transfer constant theta t as the ratio of the sending end current to the receiving end current. Okay. Also theta t is a complex quantity which is equal to AT plus J BT, where AT is called the iterative attenuation constant and BT is called the iterative phase constant. Now the fourth parameter that we have defined is the image transfer constant, that is theta I. So what is theta I? So we have to consider an asymmetrical network. So we have the input port (1) dash and the output port (2) dash. Now this asymmetrical network is now terminated by its image impedance Zi2 at the output port, that is 2 dash port. Now what is the impedance that we see from the input port? The total impedance that we see is Zi2 attached to this asymmetrical network. So as per definition of image impedance, this impedance should be equal to Zi1. Okay. So again we can define the sending end current Is and the sending end voltage Vs. Also we have the receiving end current IR and the receiving end voltage VR. Okay, so it is not possible to express a ratio of the current just like we did for iterative transfer constant here, because when we look at this network from the input side, the impedance is different. Zi1. Okay, so the ratio of Is upon IR will not be equal to Vs upon VR. So how we will define the image transfer constant is e power theta I we express as the ratio of the powers, that is the ratio of the sending end power, which is the product of the voltage and the current Vs into Is upon the receiving end power, that is the product of the receiving end voltage and the receiving end current. So this is how we will define the image transfer constant theta I. Okay, now there is one more expression we can use in terms of the hyperbolic function. So we can define tan h theta I is equal to root of ZSC1 divided by ZOC1. So this will be the same as root of ZSC2 divided by ZOC2. So this is another expression that we can use to determine the image transfer constant theta I, where ZSC and ZOC are the short circuit and open circuit impedances of this network. Circuit impedances. Okay, so we will get the same image transfer constant when we look at the network from the input side as well as the output side, and you do the short circuit and the open circuit. You can determine the short circuit and open circuit impedances and then use this equation to evaluate the image transfer constant. So after this, we have seen the case of a general T network, a general asymmetrical T network. Okay, so we have the series arm impedances ZA and ZB, the shunt arm impedance ZC. So these are the input and output terminals 1 dash and 2 dash. So we have evaluated what is the expression for the iterative impedance ZT2. So you attach an impedance Z2 to the output port. Now what is this? Z2. So we have derived the expression like Z2 is equal to half of ZA minus ZB plus root of ZA minus ZB whole square plus 4 sigma ZA ZB, where sigma ZA ZB is ZA ZB plus ZB ZC plus ZC ZA. Okay. Also, I have told that you can follow the similar lines to derive ZT1. So in that case, you have to attach ZT1 here, okay, to the input side, and you should look at this network from this side so that you will get ZT1 like this. So that could be derived as equal to half of ZB minus ZA plus root of ZB minus ZA whole square plus 4 sigma ZA ZB. Similarly, we have derived the expression for the image impedance ZI1. So we have the asymmetrical network to which we are attaching its image impedance ZI2, okay, to the output port 2 and you look at this asymmetrical network from the input side, that is from 1 terminal, you will get the impedance, its image impedance ZI1. So this ZI1 is equal to, so we have represented this asymmetrical network as a, so we have represented this network like a T network, in which we have ZA and ZB impedances across the series arm and ZC across the shunt arm like this. Okay. Now we can define ZI1 as equal to square root of ZA plus ZB ZA plus ZC divided by ZB plus ZC into sigma ZA ZB. So we have derived this. Similarly, we will be able to write the image impedance ZI2 as equal to square root of, so what is ZI2? ZI2 is when you attach the image impedance ZI1 to the port 1. Here you attach ZI1 and then you look at this network from the 2 side. Okay, so you see ZI2 as the image impedance. So that will be given by square root of ZB plus ZC divided by ZA plus ZC into sigma ZA ZB. Okay. Now we will take some special cases. So first one is a symmetrical network. So the idea here is that we can consider a symmetrical network as an approximation of a asymmetrical network. So how? So we have drawn a general asymmetrical network. You can draw like this. So we have labeled this as ZA, ZB and ZC. Now what is the case when this is going to be a symmetrical network? So this T network will be symmetrical if ZA is equal to ZB. So that is the condition for symmetry. ZA is equal to ZB. So we have discussed this in the first lecture, the condition for symmetry. So what happens to the iterative impedance and the image impedances when this is going to happen? So that we'll see. So we know the general expression for iterative impedance is that T1 is equal to half of ZA minus ZB plus root of ZA minus ZB the whole square plus 4 sigma ZA ZB. Okay, so what happens when ZA becomes equal to ZB? So this term will get vanished. Okay, so what we will have is half of, so inside the square root we will have 4 sigma ZA ZB. So that is 4 times ZA into ZB. So that is equal to, so we will assume that ZA is equal to ZB is equal to ZA. So that will be 4 times ZA square plus ZB into ZC. So that will remain change to ZA into ZC plus again ZC into ZA. Okay, so we have ZA ZC. Okay, so when you take this 2 inside, we will have the expression. So now it has become, so I'll write this as ZT1S for a symmetrical network. So ZT1S is equal to square root of ZA square plus twice ZA ZC. Okay, so that is our first equation. Now what happens to ZT2? So the general expression is, we have ZT2 is equal to half of ZB minus ZA plus root of ZB minus ZA the whole square plus 4 sigma ZA ZB. So again, when ZB is equal to ZA, okay, when this ZA is equal to ZB, which is equal to ZA, so we can write this as half of, this term will get vanished, this term will also get vanished. Again we have half of 4 into ZA square plus, that is ZA into ZB, plus ZB ZC, we can write ZA ZC plus ZC ZA again. So again we'll have the expression taking okay, we have the square root also. So we have this will be equal to square root of ZA square plus twice of ZA ZC. Okay. So this we will call ZT2 for symmetrical network S. Okay. So this is equation number 2. So what we see that when the network becomes symmetrical, you can see that the iterative impedances will have the same expression, which is equal to square root of ZA square plus twice of ZA into ZC. So that is the case for ZT2 also. Okay. Now what happens to the image impedance? So for image impedance we have the expression Z I1 is equal to square root of ZA plus ZC divided by ZB plus ZC into sigma ZA ZB. Now what happens when ZA is equal to ZB? That is a case of a symmetrical network. That is equal to ZA. So what will happen to ZI1? Let us call this as ZI1S. Now we have ZA plus ZC in the numerator divided by, now ZB is actually ZA. So we have ZA plus ZC again. And what about sigma ZA ZB? It is ZA ZB, which is equal to ZA square plus ZB into ZC will be again ZA into ZC plus ZC into ZA, you can rewrite as ZA ZC. Okay. So some simplification we can get ZI1S as square root of ZA square plus twice ZA ZC. Okay. So this is our equation number 3. Now what happens to our image impedance ZI2? We have the expression ZI2 is equal to ZB plus ZC divided by ZA plus ZC into sigma ZA ZB. So when ZA is equal to ZB, so let us say this is equal to ZA itself. So what happens to ZI2 for a symmetrical network? So this is the case of the symmetry when ZA is equal to ZB, that is the total, that is the series sum impedances ZA and ZB become equal. Okay. So in that particular case ZI2 is, you can write as square root of ZB becomes ZA, right, plus ZC divided by the denominator ZA plus ZC itself. Okay. And sigma ZA ZB can be written as ZA into ZB. So that will be ZA square plus ZB into ZC. You can write ZA into ZC because ZB is equal to ZA plus ZC ZA. So these terms can be cancelled. So we can write this as equal to square root of ZA square plus twice of ZA ZC. So this is our image impedance ZI2 S for a symmetrical network. Okay. Question 4. Now you have to compare all these 4 equations. So we can see that ZT1 is having the same expression as ZT2. right? On comparing equation 1 and 2, we can see that T1s is having the expression as T2s, so that is the same as that for I1 of s, that will be the same as I2 of s. So what is our conclusion? We can write that for a symmetrical network, we can write that the characteristic impedances, that is T1 of s, will be equal to T2 of s, that will also be equal to its image impedances I1s, which is equal to I2s, and that will be equal to its characteristic impedance Z0. Okay, so the iterative impedances and image impedances become equal in the case of a symmetrical network, which we call as the characteristic impedance of a symmetrical network. Okay. Now the next special case is that of an L network. So I have told you that we can view an L network as a special case of a T network. Can also be viewed as a special case of a pi network. So this is explained in lecture 1. So we will take the case of a T network and see how we can modify this T network to an L network. So this is the series of impedance ZA, and this is the impedance is ZB and ZC. Now how to make this as an L network? Like this. So this is our L network. So L network is basically an asymmetrical network. Let me call the series of impedance as ZA dash and the shunt arm impedance as ZB dash. Okay. So this could be transformed to, this T network could be transformed to this kind of L network by making ZB is equal to 0. So this could be made by making the series of impedance ZB equal to 0. Okay. So what is the iterative impedance ZT and the image impedance ZI for this particular L network? So this is a asymmetrical network basically. So we can define the iterative impedance ZT and ZI for this particular L network also. So how to proceed? We know the general expression for a T network. The iterative impedance ZT2 is equal to half of ZA minus ZB plus root of ZA minus ZB the whole square plus 4 sigma ZA ZB. Okay, so we make the modification. So what is the modification? So we will replace ZA with ZA dash. Okay, so ZA is replaced with ZA dash. Then ZB we will make it as 0. Okay, because there is no impedance here in the series sum here. Then what about ZC will be replaced by ZB dash. So on simplification we will get ZT2L. So that is the impedance that we get when we look at this L network with its iterative impedance is a T2L attached to this L network to the second port. Okay, that is the 2 dash terminal, and this is the 1 dash terminal. Okay. It's 2 dash. So what is T2L? That will be equal to half of, so ZA dash minus 0 plus root of ZA dash minus 0 the whole square plus 4 times ZA into ZB. So it will be ZA into 0 plus ZB into ZC, again 0 into ZB dash plus ZC into ZA. So ZC is ZB dash and ZA is A dash. So that will be ZA dash into ZB dash. So we will get half of ZA plus root of ZA square plus 4 times ZA dash into ZB dash. So that is the iterative impedance for this L network we are getting. Okay. Now we can simplify this further by taking half inside. That will be ZA by 2 plus root of ZA square by 4 plus ZA dash into ZB dash. So that is ZT2 for an L network. Now what is that is a T2. Okay. Now what is ZT1? The expression is half of ZB minus ZA plus root of ZB minus ZA the whole square plus 4 sigma ZA ZB. Right. So this is the expression for the iterative impedance for this asymmetrical T network. Okay. Now again we substitute the same expression. ZA is replaced by ZA dash and ZB is replaced by 0 and ZC is equal to ZB dash here also. So when ZA is equal to ZA dash, ZB is equal to 0 and ZC is equal to ZB dash, what you will get? You will get the iterative impedance for an L network as half of 0 minus ZA dash, okay, plus root of again 0 minus ZA dash the whole square plus 4 times ZA into ZB will be ZA dash into 0, right? ZA dash into 0 plus ZB into ZC will be 0 into ZB dash plus ZC into ZA. So that will be again ZA dash into ZB dash, right? So we can write this as half of could be written as half of minus Z A dash plus root of 4 times Z A dash into Z B dash. Okay. Okay, so that will be equal to, so you take the 1 by 2 inside, you will get this to be equal to, so that is our Z T1 of an L network as minus Z A by 2 plus root of, so we left out few terms here, so this is minus Z A square plus 4 Z A dash Z B dash. Okay, so we take the term here 1 by 2 inside, so we'll have, so this is minus Z A the whole square. Okay, so that will be Z A square, so we have Z A square by 4 plus Z A dash into Z B dash. So these are the iterative impedances for an L network. T2L is equal to ZA by 2 plus square root of ZA square by 4 plus ZA dash into ZB dash. Similarly, with respect to the port 2, we can write ZT1L as minus ZA by 2 plus root of ZA square by 4 plus ZA dash into ZB dash. Okay. So for case 2, part 1, we have seen the iterative impedances for an L network. Okay. Now we'll see the expression for image impedances. Okay. So again we start with the general expression for image impedance. So we know that for an asymmetrical T network, the image impedance Zi1 is defined as square root of Za plus Zc divided by Zb plus Zc into sigma Za Zb. Okay. Now for our this L network, we have to consider this case, that is Za is equal to Za dash and Zb is equal to 0 and Zc is equal to Zb dash. So that is how we transform the T network to the L network. So we are considering an L network as a special case of a T network when this condition is going to happen. Okay. So what happens when Za is equal to Za dash, Zb is equal to 0 and Zc is equal to Zb dash. So we will get the image impedance Zi1 for an L network as equal to square root of ZA dash plus ZB dash divided by 0, ZB is equal to 0 plus ZB dash into sigma ZA ZB. So that is ZA ZB plus ZB ZC plus ZC ZA. So ZA ZB will be ZA dash into 0 plus ZB into ZC 0 into ZB dash plus ZC into ZA will be again ZA dash into ZB dash. Okay. Now how it will get transformed? So we have ZA dash plus ZB dash divided by ZB dash into, so this term will get vanished. We have only ZA dash into ZB dash. So again we can cancel out ZB dash here and write the final expression as square root of ZA dash square plus ZA dash into ZB dash. Okay, by multiplying this ZA dash inside here like that. So this is our image impedance ZI1 for an L network. Okay. Now what about ZI2? So we'll draw the L network. So this is the L network that we are considering, which we have derived out of the asymmetrical T network. So this is ZA dash and this is ZB dash. So we have attached the image impedances to this L network. So to the port 2 dash we are attaching ZI2. So port 2 dash, and to our port 1 dash we are attaching the image impedance ZI1. Okay. Now what about the expression for ZI2? The general expression is square root of ZB plus ZC divided by ZA plus ZC into sigma ZA ZB. So this is our image impedance for asymmetrical T network. So again we have to replace ZA with ZA dash to get our L network like this. Okay. Then ZB is equal to 0 and ZC is equal to ZB dash. Okay. So this is our ZB dash. Okay. So what happens to ZI2? It will be equal to, for an L network, so ZB is 0 plus ZB dash divided by ZA dash plus ZB dash into this is ZB is equal to 0. Okay. So here ZA square, sorry, this is ZA into ZB, right? So this into sigma ZA ZB, so that will is ZA into ZB. So ZB is equal to 0, and we have ZA dash into 0 plus ZB into ZC is again 0 into ZB dash plus ZC into ZA will be ZA dash into ZB dash. So this expression will turn out to be equal to root of, so we have ZB dash in the numerator and ZA dash plus ZB dash in the denominator. So this is multiplied with, we will cancel these terms. Okay, so ZA dash into ZB dash. So what is our image impedance? Zi2 for an L network, that will be equal to square root of ZA dash into ZB dash square. Okay, so in the numerator we have ZB dash into ZB dash, should be ZB dash square, and the denominator we have ZA dash plus ZB dash. So this is our expression for image impedances for an L network. Now we will take a typical numerical problem. So take out an example. Okay, in which we are given an asymmetrical network like this. Okay, so this is an example for a balanced T network. So the application is that a normal T network that we are drawing is not balanced, because in one line we have two series elements and the other line we don't have any series elements. So in practical cases we go for this kind of T networks, which the impedances are balanced in both the conductors. So the impedance values are given as 100 ohm, so this should also be 100 ohm, and other one is 300 ohm, and this should also be 300 ohm. The shunt arm impedance is 600 ohm. So we have a balanced asymmetrical T network. Okay, and we have to find out the image impedances. For this particular network. So we know that the equation for image impedance is, so you have Zi1 is equal to the geometric mean of the short circuit impedance and the open circuit impedances. So what happens when we short circuit? So we have the 2 dash terminal and 1 dash terminal. So we short circuit the 2 dash terminal and we see the short circuit impedance is at SE1. So it's at SE1, you can see as, so we have this impedance and this impedance in series. Okay, they are in series with the entire combination of this. Okay, so we have 100 plus, so this part, that is, this part is actually parallel combination of the 600 ohm and the 300 ohms in series. Okay, so that will have, so 100 plus 600 parallel with 300 plus 300, and this will be plus 100, that is this 100. Okay, so we have, so we'll add these hundreds, we have 200s plus 600 parallel with, this is 300, parallel with 600, so that is 200 plus 300 is equal to 500 ohm. Yeah. What about the open circuit impedance is at OC1. So now this side is opened. Okay, so we'll eliminate this one. You can remove this one. So what we see the net impedance? We see the net impedance as series combination of these impedances. Okay, so C1 will be equal to 100 plus 600 plus 100, so that will be equal to 800 ohm. Now what is our image impedance is at I1? That will be the square root of 500 into 800. So we can do this, square root of 500 into 800 as 632.46 ohm. So that will be 632.46 ohm. Now what about ZI2? So the second image impedance is ZI2. So that will be equal to square root of ZSE2 into ZOC2. Second we do the SE and the OC. Of this particular network. Okay, so what will be the short circuit impedance when you short this side and you look at this network from the second port, we will get SE2. Okay, so it is a series combination of this 300 ohm and the parallel combination of this entire thing plus this 300 ohm. Okay, so we have these 300 ohms in series with the parallel combination of this 600 ohm and this 100 ohms in series and this 300 ohm. So we can write ZSE2 is equal to 300 plus 600 parallel with the 100 ohms in series plus the remaining 300. So that will be, so I add these 300s, so I get 600 plus 600 is in parallel with 200. So that will be 600 plus 600 into 200 divided by 600 plus 200. So that will be 600 plus, so can get 600 into 200, 600 plus 200. So that will be equal to 50. So we'll get Z AC2 is equal to 750 ohm. And what about Z OC2? So for this network, we remove this short circuit and we see that the open circuit impedance is the series combination of this 300, this 600 and this 300 ohm. Okay. So ZOC2 will be equal to 300 plus 600 plus 300. Okay. So that is equal to 1200 ohm. Now what is ZI2? This is the geometric mean of this 750 into 1200. So that will be equal to square root of 750 into 1200, which is equal to 948.68. Okay. Oh, so this is 948.68 ohm. So that is the example. So with that we conclude the lecture number 5. So in this lecture we have seen the characteristic parameters of asymmetrical network, that is its iterative impedance, image impedance, ZT and ZI respectively. Also we have seen the iterative transfer constant theta t, image transfer constant theta I. Also we have derived the expressions for the iterative impedance ZT and image impedance ZI for a general asymmetrical T network as well as a pi network. Okay. So after that we have viewed an L network as a special case of this T as well as this pi network, and we have derived its iterative impedance ZT and ZI. Also we have seen a symmetrical network as a special case of a asymmetrical network, and we have seen that in that case the iterative impedance ZT will become equal to the image impedances ZI. So we have ZT1 will be equal to ZT2, which will be equal to the image impedances ZI1 and ZI2, which will be the same as the characteristic impedance for that particular symmetrical network. So we have seen this also. Also we have done one numerical problem in which we have found out the image impedance ZI for a balanced asymmetrical T network. Okay. So in the next lecture we will take forward these concepts of iterative impedance and image impedances, especially this image impedance for an L network, and we will see how it could be applied in the case of a half section and what are the applications of that. Especially we will be interested in matching networks in the next lecture. Thank you.